Good morning, boys and girls, and welcome back. Today we're going to be talking about the area or the region between two curves. And here you will see we have our formula to find the area between any two curves. And that is the integral from a to b. We know different integral means area, right? Integral a to b of f of x minus g of x dx, where f of x is the top curve and g of x is the bottom curve. Here's a little picture of what we are talking about. All right, so here's our little graph. The red function, the top one again, is f of x. Okay, the top one always goes first, and then the bottom function here is g of x. And again, if we were to do this and really kind of break this down, what our little formula is saying is, if you just do the integral from a to b of f of x, a, again, is one place they intersect, and b is the other place they intersect. But if you were just to do the integral of the first part of f of x, that would give you the area from underneath the red curve, right, to the x-axis. And then if I did the area underneath of g of x, from a to b of g of x, that is the area from that to the x-axis. And again, because underneath it would be a negative number, and that's why when I go minus a negative, it would make it positive and give me the entire area under that. And you can play around with all sorts of different pictures and different ways to set this up. But you just have to know that if you always do, the top curve minus the bottom curve, that'll always give you the area between two curves. And so that's what you need to memorize and know. But here's just a picture to help us kind of visualize what's happening. All right? Okay, so here's our first example. We want to find the area between these two curves. All right. So I think the first thing you'd want to do is graph these so you have a picture to look at like we were looking at the last one there. All right. Now to graph f of x, to graph that quadratic, hopefully you recognize that that's going to be a parabola that's opening downwards. You would either need to, complete the square and put it in vertex form. You could factor it and put it in intercept form, or you just graph out a standard form, which is what I'm going to do, using x equals negative b over 2a to find the vertex. All right, so using x equals negative b over 2a, I got x is 2. And now that I know x is 2, I'm going to plug that into f, and I got 5. So I know the vertex has to be at 2, 5. Okay, so this isn't going to be perfect here, but we want kind of a decent sketch. So I'm going to go to the right 2, and I'm going to go up 5, and so there's my vertex. I know there's opening down and has an a value of 1. So over 1, down 1, over 1, down 1, over 2, down 4, over 2, down 4. So this parabola should look something kind of like that right there. Okay, close enough. And now we want to go ahead and graph our line. This has a slope of 1 and a y-intercept of 1. So this is going to look something kind of like that. And so we are going to try to find the area between these two curves right there. That's what we're looking for. All right, and to find the area between the two curves, again, it's always the top curve, which in this case, again, is f of x, minus the bottom curve, which in this case is g of x. Convenient, that works out for us. And a to b. And then a to b, again, are these points where they intersect. So I need to go find out where these two lines intersect, or these two graphs intersect. And to find out where they intersect, you are going to set them equal to each other. So negative x squared plus 4x plus 1 equals x plus 1. And I'm going to want to solve this equation. So when I set this equal to 0, I get x squared minus 3x. And I'm going to factor that quadratic, pull out a g-sub of x. And I get x equals 0 and 3. And that kind of corresponds with my picture. It looks like they're crossing at 0 and 3. So now I know I'm going to want to do the integral from 0 to 3 of f of x, which again is negative x squared plus 4x plus 1, minus g of x, which is x plus 1 dx. And that will give me the area between these two curves. All right, the next thing I would do is I would go ahead and I would simplify that expression and get 0 to 3 of negative x squared plus 3x. And now I'm ready to go ahead and integrate that. So add 1 to the exponent, divide by my new exponent, add 1 to the exponent, divide by the new exponent, evaluate from 0 to 3. And now I can go ahead and use the fundamental theorem of calculus. All right, so when I plug in 3, I get negative 3 cubed over 3 plus 3 times 3 squared over 2 minus, when I plug in 0, I'm just going to get 0 over 3 plus 0 over 2, so I just get 0. So when you plug in 0, this will happen a lot. You can just put minus 0 at the end. You don't actually have to plug it in, but just make sure it's going to give you 0 when you do that. All right, and so now I just need to go ahead and simplify that, and so that gives me negative 27 over 3, or negative 9, plus 27 over 2. And if you put those together, that's negative 18 halves plus 27 halves. This equals 9 halves as answer. So 9 halves would be the area between these two curves. All right, let's do another example. Okay, here we go. We got y squared equals negative x plus 4 and y equals x plus 2. And again, you are going to want to start out, you're going to want to graph these things. This goes back to our trig pre-calc stuff. We're going to pull back some knowledge here. But y squared minus x plus 4, that's squared, so it's still a parabola. Remember, when the y is being squared, it's a parabola that opens left or right. And because we have a negative, this is a parabola that is opening to the left. So I would probably, again, we talked about another form for this. I would probably factor out the 1, that negative 1. And that was the form we normally wrote it in. And so this tells me that this is a parabola that is shifted to the right 4 and opening left, again, because of that negative. So let me go ahead and draw that. All right, so here's that parabola shifted to the right 4, not up or down. And then we go, up 1 over 1, up 1 over 1, up 2, 4, 4, using our same normal pattern. All right. Next, we need to graph this other line, y equals x plus 2. I'm going to graph that one for us. So that would look something like that right there. We're crossing at positive 2, and we have a slope of 1. And so again, we are going to try to find the area enclosed by these two functions. So I'm going to try to find this area right in here. All right? So we said, when you're going to do this, when you find the area between two curves, you have to do a couple things. You got to find out, where you're starting and stopping, your A and the B, and you always need to do the top curve minus the bottom curve. In this case here, we kind of have some issues, some weirdness going on, because for part of this enclosed region here, the line is the top curve and the parabola is the bottom curve. But then for another part, the parabola is the top and it is the bottom, right? So if I were going to do this in terms of x's, a few things I would have to go and do. And the first thing I'd have to go and do is I'd have to go get y by itself in this first equation so that I have something that I could deal with. So if I square root both sides, this really becomes y equals plus or minus, when you square both sides, right? Negative x plus 4, I'm going to flip that around to 4 minus x. Okay? But that'd be another way for me to write this equation right here, where the positive is the top half of the parabola and the negative is the bottom half of the parabola right here. All right? And then the next thing I'm going to have to know is, where do these things intersect? So I'm going to want to set my equations equal to each other. Okay, so we know that y is x plus 2, so I took the y of x plus 2 and I plugged it in for that y there, so I have x plus 2 squared equals negative x plus 4. I then went, and you can pause and look at my work, but then I went and solved for x. All right, so now it crosses at x equals 0 and x equals negative 5. All right, so now if I wanted to set this up, this is what the equation would look like to find the area between the two curves. Okay, so if we set this up, we'd have negative 5 to 0 of the line, x plus 2, the top curve, minus negative root 4 minus x, the bottom curve. So from negative 5 to 0, the line is the top curve, and the bottom part of the parabola is the bottom curve. But then again at 0, now from 0 to 4, the positive part is the top curve, and the negative part is the bottom curve. So this would be what you'd want to set up. Now if you look at this, though, and start to think about solving this, that is going to be insane and not a lot of fun to integrate. Not fun, right? To integrate all of this stuff right here. So this is probably not the best way to go about this. There's got to be a better way, and that's what I want to show you here. All right, this better way is to integrate with respect to y. All right, and so the way I view this is, if you take your head and you tilt it to the right like I'm doing, where the positive x-axis starts to look like the positive y-axis, it's kind of what you want to do, where this is now the top of the graph and that's the bottom of the graph. That's integrating with respect to y does. That is nice because now I have the curve as the top the whole time, and the line is the bottom the whole time, and that will make things a little bit nicer for me. All right? When we integrate with respect to y, what we want to do is we want to write both of our functions now instead of terms of x and have like a dx, we're going to want everything in terms of y and have a dy at the end. So now I've got to rewrite both of these equations. I'm going to rewrite these two now, but in terms of x. Okay, so I take y squared equals negative x plus 4, and I added x to the left and subtracted y squared to the right. And so I got x equals 4 minus y squared. So this is that same function, but now we're just in terms of y with respect to y instead of with respect to x. Same thing here, I minus y, or minus 2 from both sides, and I got x equals y minus 2. And so now there's that same line, it's just written in terms of y. Right? And so now when I go to integrate, I'm going to want to integrate from, I've got to use y values, so I'm going to have to find those real fast. In a second, I'll get my limits in a second. But I'm going to have to go from here to here, from my small y value to the big y value. The top curve is the 4 minus y squared, and the bottom curve is y minus 2, dy. You can see already that this is going to integrate much nicer than that mess we had beforehand. We just got to work on our limits. We found the x coordinates, that was at negative 5 comma something, and this was at 0 comma something. We now just need to find the y coordinates. So if I plug in 0 to this equation here, 0 plus 2 is 2. That's going to be my top limit. And if I plug in negative 5 plus 2 is negative 3. So that's at the point negative 5, negative 3. Because I'm doing in terms of y, I'm going to use the y coordinate, and that was at the point 0, 2. So now I'm going to use, again, the y coordinate. And so now I want to integrate this instead, and that will work out much nicer. Okay? I will let you actually go do the math on that and do the antiderivative and work that out. But you should get 125 over 6 as your final answer. Okay? But you can see integrating with respect to y sometimes is a lot nicer. You really want to do this when you've got to split things up. I know that we had to split up to begin with. You want one integral, one top minus bottom. That is the nicest way to solve things. All right, one more question here. Okay, number 3. F of x is the cube root of x plus 1, g of x is x minus 1. So again, first go and try to graph this thing or just have a rough idea of what's going on. It doesn't have to be perfect. Cube root of x I know is like a, an S-shaped graph. Shifted to the right 1. Oh, shoot. Shifted to the left 1, but I really want this to be a minus. Sorry. X minus 1, x minus 1. They're both minuses. Sorry, wrote the problem down wrong, but it shifted to the right 1. All right? And then I know that this is a line y-intercept of negative 1, so this would look something kind of like that. All right? And again, you just need something rough to kind of look at, but the main thing that we're going to find out here is we have 2 shaded regions, right, or 2 enclosed areas that this creates. All right? So now we're going to have to kind of worry about that if it intersects more than once, because now when it intersects, on the bottom part, the line is the top, and on the top part, the cube function is the top and the line is the bottom. So they kind of switch places, so we're going to have to fix that as we set things up here. All right? So let's first find out where they intersect. So again, to do that, you're going to set the 2 functions equal to each other. Here, in this case, I would cube both sides. So I cube this side, and I got x minus 1. I cubed this side here, and got x cubed minus 3x squared plus 3x minus 1. A little bit of algebra involved in these problems. So be ready for that. Now I'm going to go ahead and solve for x. So then I set it equal to 0. I factored it. And so I had these intersect at 0, 2, and 1. And that, again, kind of look at my graph, that looks like that is about right. That's about what my sketch is kind of telling me. But I just try to verify things as I'm working. All right, now I'm going to have to set up my integrals. Okay, so for into the first area, it's the integral from 0 to 1. The top curve is the line, so x minus 1, minus the bottom curve is the cube root of x minus 1 dx, plus then the integral from 1 to 2. Now the top curve is the cube root minus the bottom one is the line. All right? And now when you do this again, please be careful. Make sure you put that in grouping form so you distribute your negative. And I'm going to allow you to work this out. You might need a little u sub, but your answer should be 1/2. And that's it, boys and girls. Thank you very much for today. See you again real soon.